Log on, tune in, find out. Another good idea from Cambridge.
I'll introduce the first speaker, who's academician Ludvig Faddeev from Steklov Institute. He is one of the icons of modern mathematical physics and also a pioneer of higher dimensional inverse problems already 50 years ago. And he's talking about using formalism of inverse problem in the theory of integrable models. This seems to be an inverse way in itself, because it's usually it was the other way around. So, Ludvig, please.
Well, it's nice to be once more in Newton Institute. I was associated with this for a long time, and now came once more. I'm a little bit embarrassed because, as last mentioned, my paper on inverse problem, last paper on inverse problem, is almost 50 years old. On the other hand, the formalism, which was developed for spectral inverse problems, for scattering inverse problems and so on, became very useful and very highly generalized in the modern theory of so-called integrable models. So in these 45 minutes, I will try to give you very short exposition of history of this development. I have written several review articles. One of them in connection with Korteweg-de Vries equation 100 years, about 15 years ago, 20 years ago already, which is called Instructive History of Quantum Inverse Scattering Method. But today I will just mention several things out of it. And then what happened during last 20 years. So the main points of this object are several papers in the end of 60s, beginning of 70s. One is paper of 4 Americans, Garden, Green, Kruskal, and Miura, at 67, about Korteweg-de Vries equation, which of course is equation for classical hydrodynamics, or used also in plasma theory, so it's completely classical theory on two-dimensional space-time, and the equation is for one function, v, so the time derivative of v is equal to v times first derivative, of course, like in Euler, and then there is a term with 3 derivatives. I'll better think with me. So what these gentlemen have shown is very interesting connection. If you consider now the Schrödinger equation, psi xx plus k squared psi equals v of x psi, where this v will be initial data for this equation. And then consider, we consider case when when this function goes to 0 at infinity. So this Schrödinger operator has continuous spectrum. The eigenfunction of continuous spectrum, psi of xk, one of them, is defined by having asymptotics like plane wave plus reflection coefficient times plane wave in opposite direction, or transition coefficient times this plane wave when x goes to plus infinity. So this means that plane wave goes from minus infinity, reflects, and transmits. Then, of course, this data, T and R, which we call scattering data, are defined by potential. So we can draw this arrow. The R itself defines T also, because T is an analytic function. There is also unitarity condition, so T is can be reconstructed when R is given. So R is enough. And then if this potential, I use term potential because of Schrödinger equation, or this velocity evolves through Korteweg-de Vries equation, then corresponding reflection coefficient will be also a function of T, but it will be, the relation will be very simple. R of high T is equal to I A k cubed T times R of k. So for logarithm of R, you have linear equation. So non-linear equation, which we began with, became linear. And you see that this k cube is, of course, comes from this third derivative. So if the first term was absent, then, of course, we would have linear equation, and which is solved by Fourier transform. Now, this map plays the role of nonlinear Fourier transform in a way. And then, of course, to solve the equation, you have to go from initial data here, then evolve R of k in simple manner, and then solve inverse problem of reconstructing the potential from R. And here the inverse scattering problem appears. For me, when I learned about it a little bit later, and unfortunately, for me it was very nice because in my candidate thesis, I was solving exactly this inverse problem, reconstructing of potential by reflection coefficient. Because before there were papers on Marchenko, Krain, Gelfand-Levitan on the Schrödinger equation on the half line, and this full line was not considered especially interesting. But in this case, it really began to work. So that's first thing. Second is interpretation of this connection by Peter Lux, who have shown that if I define my Schrödinger operator, which comes here by letter A, well, maybe he did not use L, but Lux is nature's. Then the Korteweg-de Vries equation is equivalent to condition that the L over dt, if we transform potential with time, is equal to commutator of A of L and some another operator M, which is in his case is of third order. This is second order, this is third order. So this means that the evolution of Korteweg-de Vries equation transforms Lux operator in a joint way. So the spectral characteristics are either changed or in simple way or retained exact. Next thing was, well, all right, so for years, this subject was, of course, very beautiful, very interesting, but it was looking very remote, well, very individual, just one equation, one spectral problem, and it was not clear that it's general, has more general applications. So the second equation, which was shown to be solved by this method, well, I say it's just another differential operator, which is formulated in terms of 45 minutes. I cannot write everything here. So Zakharov and Shabbat in Novosibirsk have shown that another equation is also can be solved by this method. This equation is, they call it nonlinear Schrödinger equation. It's not this besides. But you know, when we have Schrödinger, we usually use letter psi. With this nonlinear term, this equation also had applications in propagation of light in cable and so on in optics. And they have shown that this equation can be solved by similar problem, by similar recipe when the operator L was Dirac operator. Schrödinger here, Dirac here, why? So spectral problem for that operator. Of course, when psi are 0 at infinity, define as also scattering, and the similar scheme works here also. And then, final thing at the beginning of all this was my paper with Zakharov, where we have shown connection of all this formalism with Hamiltonian methods. Namely, we have observed that Korteweg-de Vries equation in fact is Hamiltonian system, of course infinite dimensional. So the function v of x give us coordinates on the phase space, which is infinite dimensional. And then Poisson brackets it must be antisymmetric. So x and y are kind of labels of our coordinates. So antisymmetric in labels, and it is first derivative of delta function, which of course is antisymmetric. And corresponding Hamiltonian is written as v cube of x plus 1/2 vx squared. Well, it's one of normalizations. I think with this normalization I must have 6 here. Doesn't matter. So we have shown that, so that's first, that Korteweg-de Vries equation is Hamiltonian. And then, of course, natural question was to write down what are the Poisson brackets for corresponding scattering data. And already you can see that in this equation, in this formula, you can see that only half of this data are changing with time, because the modulus of it's factor of modulo 1, so modulus of R is constant, and argument of K is shifted linearly in time. This is very typical picture of finite dimensional Hamiltonian systems, very typical picture of so-called completely integrable models, where you can find so-called angle action variables. So the action variables are constant in time, and angle variables are linearly changing with time. This was somehow observation which led Zakharov and me to consider Hamiltonian system. You see here the number of degrees of freedom. V of x is real function on the whole axis. R is function on the half axis. K is positive. But it's complex function, so it's 2 functions on the semi-axis, 2 real functions on the semi-axis. Altogether, it's the same. And these are angle action variables. So we checked explicitly that this Poisson bracket leads to Poisson brackets for R and K, very much like brackets for angle action variables. More exactly, if you introduce function rho of K, which is something like K over 2 pi. You know, K is now also label log of 1 minus R squared of K modulo. And so there is phi. Then rho of K, phi of L, commute like canonical variables, K minus L. So that's really angle action variables. Moreover, if you write down the energy, this functional, you see here is local functional of V and its derivatives, but in terms of rho, it became has very beautiful feature. It looks like rho times K cube Okay. But then, of course, I did not mention before, but Korteweg-de Vries equation also has soliton solutions. And soliton solutions correspond to discrete spectrum. So that's characterization of continuous spectrum. And in fact, to do proper inverse problem, you are to use relation between R of k and eigenvalues and some corresponding normalizing constants. And eigenvalues and normalizing constants also have usual Poisson relations like angle action variables. And so here you have sum of lambda cube. No, 3 halves. If lambda is eigenvalue, lambda is k squared. So this was very tempting formula. You see, it looks very much like formula for energy of field theory. It's, you know, this in the field theory, such variables rho and phi plays the role of, well, rho plays the role of number of particles. So that just particles with the dispersion law k cube, strange, non-relativistic, but anyhow. And then, but then solitons are also added particles. These are in second quantized form, and they are just as an n-particle theory. But if you consider all possible potentials, then number of particles can be anything. So you see that there appear, in one field theory, there appear many particles. First, no, two types of particles. First, which correspond to field variables, and another which correspond to solitons. So that was very impressive for me, and that's why I began to work on this and recruited in the years very bright people, altogether quite a few. I will mention Kulish first, Takhtajan, Reshetichin, Sklyanin, well, many others. It's all written here. And so the same thing for nonlinear Schrödinger looked very nice because it also produced energy much more natural, that there are particle field theory with the dispersion law k squared, and then also bound states which are characterized by this dependence of, well, analytic continuation of this k squared to bound state energies. But it was not relativistic. And during one of my visits to the United States, I was proposed to consider one more equation, which is called Sine-Gordon, which is equation for function psi tt minus phi xx. So it's now relativistic way of equation. And then term sine of phi, where m squared is a must play a role of mass. When gamma goes to 0, gamma is here, you see that you will have linear term phi. This is a massive Klein-Gordon equation, but then because phi has sine has powers, it's also self-interaction. And for that equation, Takhtajan and me developed also this scheme. We found corresponding Lux operator and excitations, and excitations were quite interesting. They were just field, of course, then there were particle solitons, and there were also periodic solutions which correspond to bound state of these solitons. And then as soon as we have such relations, you can immediately, as soon as you have angle action variables, you immediately can introduce quasi-classical quantization. And so in this quasi-classical investigation, we found with Takhtajan that this bound states has very nice spectrum, that they are written as 16m over gamma sine, once more sine, gamma n. N is number of bound state over 16. It's not in all normalization. Now, of course, people use different normalization. So, and n goes at some values. So you see that in the equation with one field, you are getting a lot of particles. And these particles are very interesting because, of course, the field degree of freedom is correspond to small gamma. When gamma goes to 0, then you are getting free field. And so that's somehow is usual field which one associate in the, let's say, perturbative paradigm. We say that you linearize the equation, and this linearized equation defines the particles, which will be massive scalar particle and nothing else. But there are also a lot of particles with different masses. And what is important that they are massive, very massive when coupling constant goes to 0. So this means that they are interacting strongly. So in one equation, a simple equation, you are getting now a lot of excitations. And you see also this duality of strong and weak interaction, which until now is reappearing in very many places. But at that time, it was Sine-Gordon. I remember that when I was lecturing about this in United States around 75, it was a great success because, of course, everything which is non-perturbative is quite interesting for quantum field theory. Very good. Then, so these were quantization, but semi-classical. So this formula, of course, is kind of approximate for small Planck constant, and so on. And so in the middle of 70s, finally we were encountered with the problem of doing exact quantization of all these things. And there were several indications that it's possible. One of them, of course, at that time were much more equations already, which were solved by inverse scattering method. One of them is so-called Toda lattice. It's discretized, model on the discrete space, and many others. And one of these things was that Adler has shown that Korteweg-de Vries equation and Constant showed that Toda lattice can be equation can be interpreted in terms of so-called co-adjoint action of Lie algebra, co-adjoint orbits of Lie algebra. Co-adjoint orbits in the theory of representations plays the role of classical phase spaces for when quantized giving representations of the group. For instance, for SU2 group, where you have Lie algebra of 3 components of spin, I will write them a little bit later, the co-adjoint orbit is a 2-dimensional sphere. It's a phase space. Spin is not a top, not at all. Spin is a variable, dynamical variable with a phase space, which is a 2-dimensional sphere. And then 2-dimensional sphere, when quantized, give you representation of rotation group. As the 2-dimensional sphere has finite volume, representations are finite dimensional, because we know that quasi-classical formula that number of states corresponds to the volume of the phase space. That's how group representation theory enters into this geometry. And then Korteweg-de Vries is also orbit, so must be quantized exactly, because representation is rather explicit formulas. Or Toda lattice must be exactly quantized, and so on. So they were it was not done, but nevertheless it was very strong indication that, well, for Toda it was even done by Constant, but for Korteweg not so, because it's infinite dimensional and so on. And well, but nevertheless there were very strong indications I think can be done exactly. And so with my students, especially with Skляnin and Takhtajan, we began to work on exact quantization. And for that, it was also important to use one more part of this formalism, namely that Lux scheme was to be substituted by so-called zero curvature formalism, namely that instead of these Lax pairs, one consider the connection, Young-Mills field, whatever, which is in 2 dimensions are just 2 first-order operators, L d over dx plus some matrix like in Zakharov-Shabat parameterized by field variables and spectral parameter lambda m d over dt plus v of xt lambda, such that nonlinear equation which you get is equation corresponding to these operators to commute. So as I say, if you interpret this as a connection in the on the space of x time, then this will be curvature of that connection, and it must be 0. So 0 curvature. And then many people, and we also began to rewrite all the previous Lax operators and so on in the form of that form. And it was not necessary that now parameter lambda is just spectral parameter in the proper sense, that it's eigenvalue of corresponding linear operator. Lambda was just to enter as a parameter. In particular, for instance, Takhtajan has written very beautiful Lax operator of the form where lambda was in denominator, so you cannot put it as eigenvalue. And you are also now interested in equation L psi equals 0. And this matrix S was exactly this one which I mentioned. Excuse me. Corresponding to spin variables S1 minus IS2, S1 plus S2, and S3 minus, where S1, S2, S3 are spin variables, which corresponds to, which has Poisson bracket that S, of course, they're all function of x, that S A of x, S B of y is equal epsilon ABC, where this epsilon is antisymmetric tensor, SC of x times delta function of x minus y. It's nice commutative relation. We call it ultra-local, that somehow only when x equals y, the bracket is not 0. This Kardec-de Vries bracket was not ultra-local, so it led to many problems to quantize it. But in nonlinear Schrödinger, for psi and psi bar, we had also ultra-local things and so on. So I have written it very clumsy. But, and of course, you can see easily that the length of this vector S1, S2, S3 is a constant, is kind of Laplacian of that relation. It commutes with everything. So you are really to be on the 2-dimensional sphere. The role of scattering data in this formalism is now was to be substituted by monodromy, which is ordered exponent, ordered because these are matrices of integrals. For instance, monodromy on the interval of minus L to L. Integral, well, I, of course, no, I is no I. I is somewhere here. U of x lambda dx, where u of x is u of xt for t equals 0, from minus L to plus L. So in field theory, we call it Wilson line. So Wilson line plays the role of scattering data. Of course, you can go to the limits when L goes to infinity, and maybe not if you don't want, then you have to consider scattering theory on the finite interval, which was done to a great extent by Sergei Novikov and his group, and also Itz and Matveyev in St. Petersburg. Well, there are also a lot of, you see, I just give you very, very short points, but each of them is connected with a lot of work somehow, or going together. And then, so the problem was to substitute this. We still call it Lux operator, in spite that it does not look at all like original Lux operator, to make this Lux operator quantized itself, namely to consider now that dynamical variables which enter here are the quantized non-commuting quantum variables. To do it in continuous case was not very easy. Sklyanin was able to do it for nonlinear Schrödinger, but for Sine-Gordon we were not able to do it, because in Sklyanin case we had this psi star and psi operators which you can put normal ordering and so on. But for phi field, which is relativistic, there is no natural. And the normal ordering would not be natural, because vacuum is not the free vacuum and so on. Well, anyhow, this was rather complicated. And so what we have done was to make discrete approximation for all these theories. So now you introduce, instead of space, instead of line as a space, introduce chain. Well, we can say lattice, but it's not lattice. It's one-dimensional. So chain, so that x in continuous limit must be equal to delta times n, where delta is this lattice spacing. And Lux operator must be substituted by Lux equation, which is this one, must be substituted by equation that psi n plus 1 is equal to L of, you see that if L is 1 plus something, then and there is delta and so on, so the derivative, well, it's somehow it reflects the conditions we had derivative here. And then in the simplest case of spin, like in Takhtajan continuous case, you see, just looking at this, at that operator, you can guess that corresponding Ln must have form something like lambda times unit. Well, I will write it differently. Lambda plus Sn3, Sn1 minus Sn2, Sn1 minus plus Sn2, and here lambda minus Sn3. Because, well, this 1 over lambda goes here, then give you unity and so on. That's very natural thing. And then this object, which is now matrix 2 by 2. But if you, for spin variables, which are quantum now, you also use two-dimensional representation, then it will be effectively matrix 4 by 4. And new connection appeared that this is Boltzmann weight for the two-dimensional classical problem of statistical mechanics for spin 1/2 variables on the lattice. On each vertex of this variable, you introduce spin variable, and you can write down different directions for these variables, somehow where they go, and altogether you get object which is called Boltzmann weight. There are several of them, and you can combine this in this matrix. Now I must tell you that I'm now doing very long story short, but realization of this interconnection of inverse problem, classical inverse problem here, and full development of these models of statistical mechanics coming from Anzager and then going to Lieb, Baxter, and other people, Young, once more come together. It was amazing. And when we realized it, when we immediately understood how to make quantum mechanics and how to introduce the quantization of this object, of monodromy, and so on. I think I will still make a short calculation and then we'll say final words. Yeah. It was realized that for that Lux operator, you can introduce commutation Lux metrics now contain 4 dynamical variables. If you write down commutators between them, you have 16 of them. And all 16 relations can be rewritten in one line. I will write this line and then explain it. R of lambda minus mu, Ln1, Ln2 of lambda and mu equal Ln2 of mu, Ln1 of lambda, R of lambda minus mu. Here, I use the following notation. Matrix L is 2 by 2 matrix in my case. So I have this space, which I call auxiliary space, equals C2. And its matrix elements are operators. So in fact, there is also another Hilbert space in which correspond to N, which correspond to that bound state, to that index. And so this relation is a relation in, if I denote L1 as L times 1, in this tensor product V times V. It's now 4 by 4 matrix. And L2 is 1 times L. And then R will be a matrix in this space. And you have this 16 relations, and R is some 4 by 4 matrix, which you can write down explicitly. It's very easily written, but I don't want to show it. These are local commutation relations for local Lux operator, but we need relations for monodromy matrix. And the trick goes as follows, that out of that equation, the relation for monodromy, which is, of course, just product of all L's, Ln, L1, in proper order, analog of that ordering. This goes as follows, what I will take out, maybe here. I will drop some letters. So consider L, Ln. Consider now product of 2 Lux operators, Ln plus 1, Ln, I write it in this order. Just multiply 2 of them and compare them with the same product in second auxiliary space. Well, observe that these 2 operators, 2 matrices, are acting in different spaces. N is different, and auxiliary space is different. And our relations are ultra-local, so that operators here and operators here commute. Only when n are equal, they are not commuting. This attracts delta, reflects the delta function in relation for spins. So you can rearrange them. You get R, Ln plus 1, 1, Ln plus 1, 2, and Ln 1, n plus 1, 1, ln 2. Now you can use the fundamental relation which I have here. You take r through this and to take r through this. You are getting ln plus 1, 1, ln 2, mn plus 1, 2, ln plus 1, excuse me, 1. No, excuse me, I was a little bit. It was 2 here. It was here. No, 2. Ln plus 1, 2. Yes, ln plus 1, 1. ln 1, ln 2. Yeah. So when I substitute it, now it's 2 here, 1 here, 2 here, ln here, ln 1 here, times r. And now you can interchange this once more. Нет, что такое? Let me take it. I'm already a little bit tired. So this is all right, yeah? Now I write ln plus 1, 2, ln plus 1, 1, ln 2, ln 1 times r. And now I interchange these things once more, and then I'm getting ln plus 1, 2, ln 2. You see this type of combination. ln plus 1, 1, ln 1 times r. So the product of these two l's satisfy the same relation as L themselves. And now you multiply many times. And finally you will get relation that R T1, T2 is equal to T2, T1, R. No work, you just pure, very simple algebra, which give you commutative relation for monodromy, which is very non-local functional of all these field variables in terms of all these of local operators. So this allows us to control monodromy, to introduce now spectrum of monodromy and so on. It's once more a very long story. Have taken a lot of time, but I just want to show you that how formalism is working. And finally, well, of course, if you look properly on this exercise which I have done, you see that you're dealing with some object which is called Hopf algebra, because I'm interchanging, I'm showing that the same relations which are valid for algebra generated by Ln is also valid for product of this Ln, of two algebras. Product of two algebras is called coproduct, and so the Lax operators, in fact, somehow are generators of Hopf algebras. This was taken by more, this idea was taken by more mathematically minded people like Drinfeld, and so Drinfeld understood that what we are doing is some field in the Hopf algebras, which at that time was very remote part of mathematics, because they did not know good examples. So this problem produced a lot of beautiful examples for people doing this algebraic topology. They were very excited because they did not have any examples of Hopf algebras which were not commutative and non-co-commutative. And Greenfield coined the term for related object, which is now very popular, which is called quantum groups. So you see that this formalism from very applied mathematics led to very highbrow mathematics and introduced new object which until now is developing and acquires a lot of applications. Well, I think I must finish now. So let me just quote what I have written almost 20 years ago and then say 2 more words. Thus, the final trick found in applied plasma physics on the example of Korteweg-de Vries equation, being gradually developed in mathematical manner with quantum mechanical applications in view, threw new light on the methods of many body problems in solid state physics, crystallized in several fundamental formulas and led to new mathematical structure with a host of unexpected applications, including that in modern physics of elementary particles. And well, I say that it's still developing, and so I hope that there will be new applications. And now, just last 10 years, we see that integrable models became kind of centerpiece of new exercises which is done in the laboratory of modern theoretical physicists, string theory. I say laboratory because it's still not physical, but nevertheless it somehow is a very interesting subject which led to a lot of unexpected mathematical connections. So I think that it's very unprecedented example of history of relations of physics and mathematics, and these things are continuing. Thank you very much.
Questions? Matti?
Like this Faddeev spin function is a central object now in our study of Schrödinger equation. So I mean, is there analog of your spin function? This could have
No, until now, in the formal approach, integrable models are all two-dimensional, x and time. But then you see we have discrete system with n, and n could be a label of something which is operator in four-dimensional case. So in the modern, one of the applications of integrable models to strings is when n is just number of operators which you multiply in the chain. And they are operators in the six-dimensional space-time and so on. So there are, but nevertheless, the structure is that you have two, x and time. Now you can say there are three-dimensional discrete systems like Miva, well, Hirota lattice and so on. It turns out that it's still two-dimensional, and one of directions is discrete, so two directions are space and time discretized, and third direction is the Dynkin diagram for the corresponding group. So you have your dynamical variables are not scalar, but have many indices themselves, and so on. The four-dimensional self-duality equation is also two-dimensional. Two variables there are space-time in sense of integrable models, and other two variables correspond to some infinite dimensional groups with which you parameterize things. So two dimensions is very essential.
Actually, my question was similar. I was asking if you start with a multidimensional Schrödinger equation.
Nothing.
You actually asked.
Well, until now, nothing is of that time is good. So you see this zero curvature is kind of two-dimensional. Well, for a long time, we were just said, well, all right, beautiful, but nevertheless, you are two-dimensional, what's going on? But now new applications are all many-dimensional, so but they are more sophisticated, not just space-time. Yeah.
More questions? If not, we are ready for coffee, and we come back at 11:15. Thank you.